Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please help support us on Patreon if you can, and don't forget we have Academy-themed merchandise in the Academy store. There are links in the description, and we appreciate you. We try to devote most of our time to non-military applications of space science, but sometimes world events force us to help explain a space-related military concept. On the 18th of March, 2022, history was made. On this date, the first hypersonic missile was used in war. The missile was a Kinjal or dagger missile, called Killjoy by NATO. This missile was released by a MiG-31K interceptor. The MiG-31K can fly at speeds up to Mach 2.8, faster than any Western military aircraft currently deployed. The missile has a range of 2,000 to 3,000 kilometers and can be launched from the MiG-31K, which can carry one missile, or the Tu-22M3. The Tupolev 22M is a supersonic swept-wing bomber, similar to the American B-1, and can carry up to 4 Kinjal missiles. The Kinjal reaches speeds of Mach 10 to 12. This is about 14,700 kilometers per hour, or around 9,130 miles per hour, under standard conditions. This missile can carry a 500 kilogram high explosive fragmentation warhead or a 500 kiloton nuclear bomb. What is the significance of this development? And how worried should the West be about this missile system? Let's look at the science behind hypersonic flight, the threat posed by hypersonic military weapons, and the civilian space applications of some of this technology. Anything above Mach 5 is considered hypersonic. This only counts if you are within the atmosphere, usually considered anything below 90 kilometers. That means anything above 100 kilometers is considered space, the International Kármán line, and anything below 90 kilometers is in the atmosphere. Let's call the 10 kilometers in between subspace. The first human-made device to go hypersonic was a rocket, launched from the White Sands Missile Range. This rocket had 2 stages. The first stage was a V-2 rocket, captured from the Germans at the end of World War II. The second stage was a WAC Corporal rocket. The second stage of the rocket survived the atmospheric flight and flew on into space, reaching a maximum altitude of 403 kilometers. Falling back in a vacuum, it reached a velocity of 8,288 kilometers per hour. This is over 5,000 miles per hour. The rocket materials could not survive the heat generated at this speed and burned up into small fragments. Other similar rockets were fired at a low launch angle to study hypersonic flight. Supersonic flight is anything above Mach 1. Some researchers now like to say that anything below Mach 0.65 is subsonic, 0.65 to 1.35 is transonic, and over 1.35 is supersonic. Others say the limits are 0.8 to 1.20. The distinction is important because as we approach Mach 1 speed, the airflow over the vehicle varies, because airflow accelerates on convergence at subsonic speeds, but accelerates on divergence at supersonic speeds. We get rapidly changing and variable airflows over the ship's surface at transonic speeds. The transonic period is very dangerous for aircraft. This was one of the things that helped bring down the Virgin Galactic Spaceship Two Enterprise, killing the co-pilot, Michael Alsbury. Most rockets go through this transition zone so quickly that the point of maximum dynamic stress, called max Q, is much more dangerous to them than breaking the sound barrier, and is based on the speed of sound in a specific gas at a specific temperature. There is no easy way to convert Mach speed into a comparative velocity, like kilometers or miles per hour. Mach speed will be different depending on the composition of the gas we are flying through and its temperature. For instance, in standard Earth atmosphere, at 20 Celsius, which is 68 Fahrenheit, the speed of sound is 343 meters per second, which correlates to 1,235 kilometers per hour or 768 miles per hour. As an object approaches Mach 1 velocity, a shockwave forms in front of it. This shockwave forms because the air molecules can no longer get out of the way and start being compressed. Next to the skin of the ship is a stationary layer of air. This is called the boundary layer. Past this is the shockwave. As speed increases, the shockwave compresses the air more and more. Compressing a gas causes it to heat up, and the temperature in the shockwave is higher than the ambient temperature. The first human-flown aircraft to travel above Mach 1 and survive is usually reported to be the Bell XS-1 in October of 1947, with Chuck Yeager piloting. There is, however, reasonably good evidence that an XF-86 Sabrejet, piloted by George Welch, had broken the sound barrier earlier, at least twice, while in a powered dive. If this is the case, it was not well documented, and such evidence is referred to as anecdotal. So we can say without reservation that the first verified level supersonic flight of a human-operated aircraft was the Bell X-1. The first human-operated hypersonic flight was by this aircraft. This is a rocket-powered airplane called the X-15. The X-15 was flown to high altitude by a B-52 bomber, then dropped. The hydrogen peroxide-powered turbopump sent the ammonia fuel into the XLR-99 rocket engine. And in November of 1961, Air Force Major Robert White flew his X-15 at Mach 6. This was the first documented hypersonic flight by a human-operated aircraft. At this speed, the shockwave compression causes very high temperatures. These equations would allow us to calculate the shockwave conditions in a theoretically perfect gas. In these equations, P stands for pressure here, while this symbol is ρ, standing for density. T is for temperature, M is the Mach number, and this symbol, gamma, is the specific heat ratio. This value is usually 1.4 in normal Earth atmosphere. If we know the Mach speed and the ambient temperature, we can use this equation to calculate the normal shockwave temperature. The term normal shockwave means perpendicular to the direction of flight. In real gases, the equations get more complicated, and we can use a normal shock table. This tells us that the downstream temperature at Mach 1.01 is just 1.0066 times the upstream temperature. This is negligible. Now let's go to the end of the table, Mach 5. Here we see that the downstream temperature is now 5.8 times the upstream. So a comfortable 20 Celsius, or 68 Fahrenheit, becomes a boiling 116 Celsius, 241 Fahrenheit. Almost all aviation materials can survive this temperature, though you might have to worry about overheating your pilot. To look at hypersonic temperatures, we need to use a different table. I found this one in the digital library. There will be links in the description. Here we see the ambient temperature. These are in Kelvin. So this 283 Kelvin is about 10 Celsius or 50 Fahrenheit. Here we see that Mach 6 is 2000 Kelvin. This is over 1700 Celsius. Pure aluminum is listed as having a melting temperature of over 600 Celsius. And in the Earth's atmosphere, we have to worry about oxygen. Heating something in a vacuum is very different than heating it in oxygen. As the shockwave compresses and heats the atmosphere, oxygen molecules get torn apart into free oxygen radicals. Free oxygen is one of the most destructive, corrosive substances possible. The free oxygen will tear atoms of metal away, forming oxides. Steel will start burning in air at 1230 Celsius. But at about half that temperature, it will start to dramatically weaken. The X-15 survived the heat generated by its hypersonic flight because it was made of a special alloy. This alloy was called Inconel X, which was mainly nickel and chromium. It also used its fuel to actively cool the ship. Ammonia is an excellent coolant. The Kinjal missile reaches up to Mach 12. Let's look at our hypersonic tables again. They show the temperature for flight at an altitude of 46 kilometers with an ambient temperature of 10 Celsius. Ukraine in March had an average temperature of minus 1.3 to 7 Celsius, not far off. So the Mach numbers will be close to the same, since it is mainly determined by gas temperature. But the elevation of Ukraine is only 0.63 to 1.72 kilometers. The atmosphere here will be much denser than where this test table was conducted. Air is normally 21% oxygen, 78% nitrogen, and 1% argon and trace gases. So there will be more oxygen and nitrogen molecules per cubic meter at a lower altitude, creating a higher dynamic stress, or Q, and a higher oxidation rate. The Kinjal will produce a plasma shock wave at this temperature as it flies. This would be a big problem for a reusable spacecraft, but a hypersonic missile will of course be used only once. The Kinjal has been designed to withstand these conditions, during its short lifespan. The Kinjal uses solid rocket propellant to achieve hypersonic speeds. Even without a warhead, this Kinjal would hit a target with a force equivalent to 4,000 kilograms of TNT because of its tremendous kinetic energy. The 500-kilogram warhead at the end of the missile is designed to survive the impact and explode deep underground. This allows it to destroy buried and reinforced military targets. That is why it was used in Ukraine. The missile was sent to take out an underground weapons bunker. Lots of bunker-busting bombs exist that could do the job. The problem for Russia was that the Ukrainian air defense systems have managed to keep the Russian forces from controlling the skies. Some of the ground-based anti-aircraft missiles hit speeds of Mach 5. Anti-aircraft missile systems can take out almost any airplane they can track. And handheld anti-aircraft missiles provided by Europe and the United States have proven very effective. And against an airplane flying at less than Mach 3, it's not too difficult to hit them. The fastest air-breathing aircraft ever was the SR-71 at Mach 3.2. But a missile coming in at Mach 10 or 12 is another matter. At this velocity, the slower anti-aircraft missile may not be able to maneuver fast enough to intercept. When Russia claims that these missiles are unstoppable, however, they are mistaken. Hypersonic interceptor missiles would have a chance of taking them out, and there are other options. The United States has built and deployed laser defense systems. These fire powerful bolts of coherent energy at the speed of light and could burn through an incoming hypersonic missile, exploding its propellant or warhead and destroy it. The rest of the missile would break up rapidly from dynamic pressure. This would best be accomplished by a laser positioned off to the side. But lasers don't work very well in atmosphere, and they could only effectively destroy a missile once it got fairly close. Also, the plasma produced by the shockwave would actually shield the front of the missile from the laser. And if laser defenses become more common, reflective or reactive anti-laser armor will be developed. But these add to the mass of the missile and slow it down. By the way, it is best to put your avionics further toward the back of the missile, as the plasma shockwave can block radio signals, including GPS or the Russian GLONASS system. The Kinjal, while rather simple, is right now the most effective hypersonic missile deployed to date. Other nations are also working on hypersonic missiles. The U.S. had done a lot of research on hypersonic flight in the 1990s and early 2000s. The X-43A was dropped from a B-52 bomber and boosted by a Pegasus rocket to fly at Mach 9.6 in 2004. The Boeing X-51A scramjet-powered Wave Rider flew at Mach 5.1 from 2010 to 2013. It seems like this might be moving backward, but the U.S. was studying long-range hypersonic cruise missiles. The specific impulse of air-breathing engines is much higher than solid rocket motors. A liquid-fueled air-breathing hypersonic missile would allow the airplane to launch it from a much greater distance, keeping the airplane safe from enemy interception. The United States tested its new Hawk missile the same month the Kinjal was used. Hawk stands for Hypersonic Air-Breathing Weapon Concept. It launched from a B-52 off the coast of the United States. The booster rocket took the missile up to speed, and the scramjet took the missile up above Mach 5. The United States argues that the Hawk missile is more advanced than the Kinjal, arguing that the Kinjal is just a modified Iskander tactical ballistic missile with a more powerful booster. And to a degree, they are right. But anything that gets the job done now is much better in warfare than a more advanced system that will work someday. The Nazis learned this when their few rockets and jet-powered flying wings kept getting blown up by thousands of much less advanced propeller-driven bombers. While the Kinjal is a direct threat to our NATO allies, it is not at all a threat to the continental United States. But the Kinjal is not the only hypersonic weapon Russia is working on. They're also looking at adding hypersonic glide vehicles to their ICBMs. We mentioned this in our lesson on the Satan II ICBM. A boost glide system is when a spacecraft is boosted in an arc above the atmosphere by a rocket, using gravity to accelerate it further as it comes back down. These re-enter the atmosphere at extreme hypersonic velocities, up to Mach 25. Then they use aerodynamic surfaces, specially designed to work at hypersonic speeds, and thrust vectoring to change direction of travel. evading defense systems and confusing interceptors, gliding on to a more distant target. The Russian boost glide vehicle is called a Vanguard, previously known as Object 4202. The name in English is almost the same, Vanguard, the forward unit of a fighting force, what the U.S. calls the tip of the spear. This vehicle can be deployed by several rocket systems. It can deliver both conventional and nuclear warheads. This system was tested in 2015 on a UR-100 ICBM launched from Dombarovsky Air Base, and it reached a speed of 11,200 kilometers per hour. In 2016, one was launched on an R-36M heavy ICBM from the same base, accurately hitting a target at the Kura missile test range, and reportedly hitting speeds of Mach 27. In 2018, Russia started deploying these to its strategic rocket forces, and in 2019, the first Vanguard became combat ready. The US and Russia are not the only players on the hypersonic field. China is a true leader in this category also. China has tested a long-range missile that circled the entire Earth and released a hypersonic glide vehicle that accurately impacted a target in China. These missiles would be a lot harder to intercept, but they should not be undetectable. There's a lot of talk in the media right now about how one of these could sneak up on the United States. This is a possibility, but these ultra-fast missiles generate a very hot shockwave. Infrared sensing satellites could track these from orbit. It may be that the United States is keeping its velocity lower, so as not to create a trackable shockwave. Combined with the United States' clear superiority in stealth technology, and you could have a hyper-fast, near-radar invisible cruise missile that could be launched far from enemy territory. But warfare is not the only use for this technology. Helium-3 mined from the moon could be launched toward Earth by a mass driver in one of these vehicles. It could then re-enter and glide to a safe landing spot, slowing down and deploying a parafoil, like the one designed for the Mercury astronauts, to land at a designated spaceport. This would be the cheapest way to receive high-value cargo from a colony on the moon. But a glide vehicle does not have power. Powered hypersonic flight would enable intercontinental travel in just a few hours. Companies around the world are looking to hypersonic transport. Many companies have great ambitions and good CGI, but we could only find one that looks like it's about to fly. This is the Halcyon Hypersonic Transport, designed by Hermeus Corporation out of Atlanta, Georgia. Hermeus was founded in 2018 and put together a team with amazing experience, as you can see here.
You probably don't have to ask me why I joined the Hermes board of directors. You get to build a hypersonic airplane. Who's going to say no to that? One of the last things I did before leaving government service is take a picture with the A-12 in front of the CIA's headquarters. I love that period of aviation and particularly love that airplane. The fact that it still holds so many records for high-speed flight for an airplane that is now many decades old is a really sad statement. What happened to high-speed aviation? Why did we quit pushing on it? There is a desire being driven not just by the Air Force or me when I was in it, it's now being pushed even at the presidential level to speed up transportation, to make points on the globe closer together in time if they can't be closer together in distance. So pushing beyond Mach 1 plus travel, which has already been done, been there, done that, and the Concorde's not here anymore. And now only militaries fly above the speed of sound, but only getting back to where we were does not achieve that vision that President Biden spoke of. We've got to go much faster. And so Hermeus has picked a very good design where that first step into really high Mach numbers will completely change the way transportation can be done in future, but without having to be built of unobtainium. Right? The tech that they've picked will be challenging, but not impossible to integrate together. And I think Hermeus has laid out a great plan to crawl, walk, run, fly, and sprint their way to that goal line. And I'm delighted to join their board and to help them achieve their vision.
So what goal do we set in hypersonics today? Hypersonics needs a unifying vision. That vision should be accelerating the global human transportation network. Our goal is to complete that challenge, to fly passengers across oceans at hypersonic speeds before this young decade is out.
Ladies and gentlemen, meet Quarter Horse.
If everyone could please take the headsets, the ear protection is currently being handed out. If you have a noise sensitivity, feel free to step inside. But if not, this is definitely something you're going to want to see and feel.
Ignition confirmed. Command throttle to 103. Copy. Throttle to 103. Back, baby.
I joined Hermeus because I've spent a lot of time thinking about US strategic competition with China. And to me, what is critical to this competition is technology. Ultimately, the US will win or lose based on whether it can leverage companies really at the nexus of commercial innovation and national security. And when I came across Hermes, I thought, this is a really cool company that's right in that sweet spot. And so I thought, let me roll up my sleeves, get my hands dirty, and really jump in and make a difference. My background is quite diverse. I've spent time deployed overseas as an officer in the US military. I've spent a great deal of time at think tanks looking at really every angle of US strategic competition with China. I've also served at the Pentagon as well. So I hope to leverage all these diverse experiences in my new role here. My primary job here is going to evolve very rapidly as the company is growing at a pretty almost exponential pace. First and foremost, it will be the voice and ears of Hermes on the ground in DC. I will be our first kind of permanent person in our nation's capital. And a lot of my role will really be trying to understand how can we work most closely with government and develop products that are going to have that kind of national security application. Hypersonics is a really interesting field that the US is dedicating enormous resources to, with a particular focus on offensive strike. But what drew me to Hermes is that we're looking at hypersonics from a slightly different angle, which is reusable high-speed flight. And this is an area that is really engineering, it's not science. The technology is mature. And there's enormous potential for the US through kind of innovative public-private partnerships to build out a whole new industry and to really jump forward and be a world leader in this space. So to me, hypersonics is interesting because it's an area where the US can really leap ahead, again, in this kind of competition that's unfolding.
The whole space of space and aviation has opened up to startups. These used to be national programs. Now, most of the innovation is coming from young entrepreneurial teams with a real passion for what they're doing. There's a lot of startups, but very few who are really pioneering with clever strategies. SpaceX definitely did that, Rocket Lab did that, Hermes is doing that. Hermes has been very, very entrepreneurial, very clever strategy. Most people attempting something like this are talking about multi-billion-dollar engine designs and a decade and more of huge uncertainty. Hermes had a very short path to proving the key risks out and then going to market in a national defense context. That is both very valuable for Hermes as a revenue generating company and to the nation as a whole. It is a great hack to get to revenue faster and make a real contribution faster. You know, all the companies I mentioned are American mostly. There's a few efforts overseas, but most of the innovation is American because of this American culture of entrepreneurship. If we're going to keep up with the Chinese in hypersonic flight, almost certainly it'll come from an entrepreneur here. not a contractor waiting for guaranteed payouts before they do things. So going at risk, which Hermeus is doing, developing things on their own nickel, that's all what accelerates things, and that's what lets us compete effectively with other national programs, especially countries that might be ahead of us to start with. It's always exciting to see how much entrepreneurs can do. They take something that's impossible, make it possible and then probable, and then really make it happen. And I think that's the story we are hoping for here from Hermes.
Within 9 months, this amazing company had built and tested this. This is Chimera. Chimera is a Mach 5 air-breathing engine. Here you can see it in operation. And here you see how it is installed in a test run. This ship is called Quarter Horse. It is a smaller proof-of-concept aircraft built to test the Chimera engine. Here you see the air intake and a precooler, as the turbine could not withstand the heat of hypersonic flight. Then the turbojet itself and a ramjet afterburner. A ramjet afterburner allows the engine to run fuel-rich through the turbine, keeping it cool. Then they can add oxygen back here, just as the airflow is leaving the engine. Since the fuel burns after it goes through the turbojet, it's called an afterburner. This aircraft would take off horizontally, fly through the sound barrier up to Mach 5. Here you can see where the engine flies up to current jet engine limits, then uses both the turbojet and ram burner to climb higher and go faster, engaging the precooler as the velocity heats the incoming air. And finally, using the ram burner only, as it exceeds Mach 2.8, taking the ship on up to the top speed of Mach 5. How does this ship survive a speed of Mach 5 and maintain flight for a range of 7,400 kilometers? For one thing, it's made out of the same amazingly strong and lightweight metal as the SR-71, titanium alloy. Titanium alloys are very strong, heat-resistant, and lightweight. Here you can see the ram scoop that becomes critical at hypersonic velocities. Once the ship reaches a high enough velocity, you no longer need a turbine to compress the air. The speed of the ship does that for you, and you don't need to cool the air if it's not going through a turbine. Once you reach this speed, you can just dump fuel in here, pushing the ship faster. This engine design will allow the passenger-carrying Halcyon to fly from New York to Paris, a journey that normally takes almost 8 hours in just 90 minutes. I would keep a close eye on this company. We may be booking flights with them soon. Is there any way to go even faster? This is a SpaceX Super Heavy booster, and I'm adding a powered hypersonic transport craft. This system would boost the hypersonic transport to the other side of the Earth. On reentry, it could use vectored thrust and aerodynamic surfaces to direct itself to a landing zone. But re-entering the atmosphere at Mach 25 generates a lot more heat than flying at Mach 5. It generates a 20,000 Kelvin shockwave, in fact, which would transmit enough light through the boundary layer to generate a temperature of 1,650 Kelvin on the surface of the ship. Not even titanium could survive this temperature. We could use the amazing copper alloy called GR-COP42, developed by NASA in the 90s and used to create the Pangea aerospike engine described in this lesson. But there might be something even better. NASA has started nanoprinting different metals into alloys that would be impossible to produce by any other method. This is GRX-810. It is an oxide dispersion strengthened alloy, and it has more than 1,000 times the high temperature and high stress durability of competing alloys. It also has twice the resistance to fracturing and is 3.5 times more flexible. AI-driven thermodynamic modeling, combined with 3D nanoprinting, will produce amazing new alloys. New alloys like this can improve the efficiency of rocket engine turbines and turbojets. This same technique will someday be used to 3D print nanoscale alloys that conduct heat like GRC-42 while surviving high oxygen stress like GRX-810. And then we can safely travel from one side of the Earth to the other in less than an hour. Something to think about. Thanks for listening, and stay safe. At Astra Pro Terra.